Hello everyone, welcome to the fifth session of VSSP. Today we have with us Miss Jyoti. She is one of the founding members of Curryleaf and she is also the most dedicated, enthusiastic and energetic person in the club. She has done her BSc and MSc from NSCBM Government College, Hamirpur, Himachal Pradesh. Currently she is first year research scholar at NIT Hamirpur, Himachal Pradesh. She has attended MTTS level O at RIE Ajmer in 2019, MTTS level 1 at 2020. She has been mentor of OFCM in 2020 and as well as 2020. Over to you, Jyoti.
Yeah, thank you for the invitation. And now I would like to invite Mamta Adhikari. So Mamta Adhikari is pursuing BSc in Mathematics from Nar Bahadur Bhandari Government College, Tazun, Sikkim. And her topic of presentation is rank nullity theorem. So Mamta, over to you.
Okay, so hello everyone. Today I'm going to have a talk on the topic rank nullity theorem and its application. So let's see what does this theorem states. So let V and W be two finite dimensional vector space and T is a linear transformation from V to W. Then the dimension of V is dimension of image of T plus dimension of kernel of T, which is equal to rank of T plus nullity of T. So this is the definition of rank nullity theorem. So before going further into the proof, let's see some important terms. That is, what is meant by dimension, basis, image of T, kernel of T, rank of T, and nullity of T. First of all, let me explain what is basis of T. So given any set of vectors is called a basis if it is spanning set and it is linearly independent. So after that, I'm going to discuss what is dimension of vector space V. The number of vectors in a basis for V is called the dimension of V, denoted by dimension of V, where V is a vector space. So dimension of a vector space is nothing but the number of vectors present in the basis of that particular vector space. So this is what meant by dimension. Secondly, we'll discuss what is meant by rank of T and nullity of T. So rank of T is dimension of image of T and nullity of T is dimension of kernel of T. Now again we are going to discuss what is image of T and kernel of T. So let's see what do we mean by image of T and kernel of T. So by taking an example, I've shown this, that let T be a linear map from V to W, then the image of T is defined as all those small w in W such that there exists V in V such that T of V is W. From here, we can say that image of T is a subspace of W. And since we have earlier in the definition of the theorem, it is written that V and W are of finite dimensional. That means W is finite dimensional and its subspace, which is image of T, should also be of finite dimension. Let's see what is meant by kernel of T. Kernel of T is all those small v in V such that T of V is mapped to the zero vector. So kernel of V is the subspace of V, and again the same logic that V is of finite dimension and its subspace should be of finite dimension. So since both the vector space, that is V and W, and its subspace, that is kernel of T and image of T, are of finite dimensional, we can talk about their basis also, that there must exist some basis for that particular vector space. Now I'm going to, this is what I've told earlier, that range of T and kernel of T are subspace of W and V respectively. Hence, since they are subspace of W and V, and since W and V are finite dimension, its subspace should be of finite dimension. Now, after seeing all these terms, now we would go into the proof. So, my proof starts with where I have assumed that the basis, the set U1, U2, UK be a basis of kernel of T. Since this is a basis of kernel of T, this set is linearly independent and it is a spanning set. And then, since kernel of T is a subspace of V, there exists a theorem that every linear independent that this linear independent set can be extended to a basis of its subspace. So we can extend this basis to a basis of its subspace, that is V. Therefore, this can be extended to a basis of V, say U1, U2, UK, and V1, V2, Vn. So, by the definition of dimension of kernel of T, if U1, U2, UK is a basis of kernel of T, then we can say that dimension of kernel of T is K. And again, if U1, U2, UK and V1, V2, Vn is a basis of V vector space, then we can say that dimension of V is K plus N. Now, dimension of V is K plus N, where K is a dimension of kernel of T. That is, dimension of V is dimension of kernel of T plus N. So, if we are to prove this theorem that dimension of V is equal to dimension of image of T plus kernel of T, I need to prove here that N is a dimension of image of T. So, if I have to prove that N is a dimension of kernel of T, I need to prove that this TV1, TV2, TVN is a basis of image of T. That is, this TV1 spans image of T and it is linearly independent. This is by the definition of basis. So, firstly, we would show that this TVI spans image of T. So, in the first case, we show that this spans image of T. So, we pick any arbitrary element, let's say small w, which belongs to image of T. That means there exists, this is by the definition of image of T, there exists V, small v in capital V, such that T of V is W. Since V belongs to capital V and U1, U2, UK and V1, V2, Vn is a basis of capital V, we can write this small v in linear combination of this basis. That is, V can be written as summation I running from 1 to k, alpha I, ui and summation j from 1 to n, beta j, vj. We can write this small v in this form. After writing this small v in this form, we can simply put the value of small v in w. So, our w becomes T of v such that this can be written as T into summation I running from 1 to k, alpha I, ui plus summation j from 1 to n, beta j, vj. This is equal to summation I from 1 to k, alpha I, T of ui plus summation j from 1 to n, beta j, tvj. This is by the property of linear transformation. Since T is a linear transformation, we can write in this way. This first term, that is summation I running from 1 to k, alpha I of ui would be 0. Since ui belongs to kernel of T and T of ui would be 0. So this the whole term, that is summation I running from 1 to k, alpha I, T of ui would be 0. So we would be left only with summation beta j, T of bj. Now we have picked any arbitrary element from the image of T and we have shown that this arbitrary element can be expressed in the linear combination of this TVI. This implies that TV1, TV2, TVN spans image of T. So we have already proved that this TVI spans image of T. Now we need to show that this TVI is linearly independent. So we prove that this TVI is linearly independent. Now our claim is this TV1, TV2, TVN is linearly independent. So in order to prove this, we would let that linear combination of this TVI is 0, such that summation I from 1 to n alpha I t of bi is 0 for some scalar alpha I. Then, since by the property of linear transformation, since T is a linear transformation, we can write this as T summation I from 1 to n alpha I vi would be 0. T of summation I running from 1 to n alpha I vi is 0. This means that summation I from 1 to n alpha I vi belongs to kernel of T. Since this belongs to kernel of T and we have a basis of kernel of T, that is u1, u2, uk. So this particular term can be represented in the form of linear combination of the basis of kernel of T. Since u1, u2, uk is a basis of kernel of T, there exist scalars beta I such that summation I running from 1 to n alpha I vi can be is equal to summation j from 1 to k beta j uj. So after this, bringing this right hand term towards the left, we would get summation I from 1 to n alpha I vi minus summation j from 1 to k beta j uj is 0. Now, this linear combination of u1, u2, uk and b1, b2, bn is 0. That means this since this u1, u2, uk and b1, b2, vn is a basis of v and its linear combination is 0, then it is clear that alpha I is 0 and beta I is 0. Since basis is a linearly independent set, so alpha I and beta I should be 0 for all I and k. So we have shown that this TVI is linearly independent set, and in the in previous we have already shown that this is also a spanning set. Since it is linearly independent and spanning set, so we can say that this is a TVI is a basis of image of T. Since it is a basis of image of T, we can say that this is a dimension of image of T is n. So dimension of V is n plus k, which we got n is dimension of image of T and k is dimension of kernel of T. Dimension of image of T is rank of T as we have discussed earlier, and dimension of kernel of T is nullity of T. So in this way, our theorem is done. So now we would see some of the applications of this theorem. So let's see this application. Now we wish to find the range and kernel of a linear transformation that is T from R2 to R2 defined by T of xy is equal to x plus y, comma x minus y. Now, rank nullity theorem has many applications. Like we can find kernel of T and then say that is the range of that particular transformation would be this. Again, we can find range and we can say about kernel. So now in this case, we would find kernel of T. So by the definition of kernel of T is the set xy belongs to R2 such that T of xy is 0, 0. That is, T of xy is mapped to the 0 vector. So by the way the linear transformation is defined, we can write x plus y is 0 and x minus y is 0. So this implies x equal to minus of y and x equal to y. X equal to minus of y and x equal to y, this is true only for x is 0 and y is 0. Therefore, kernel of the set kernel of T is the 0 vector only. Therefore, dimension of kernel of T is 0. Now we got that the dimension of kernel of T is 0, and by rank nullity theorem, what we know that if the dimension of image of T would be 2. Why? Since dimension of R2 is 2. which should be equal to the nullity of T plus rank of T. But here, since we got that the nullity of T is 0, therefore rank of T must be 0. So this is one of the applications of rank nullity theorem. Let's go further to see the other example. So this is the other example. Let T be a linear transformation from R3 to R3 defined in such a way that T of xyz is equal to x plus y plus z, and z plus x for all x, y, z belongs to R3. Then determine rank and nullity of T. So similarly, like we saw in the previous case, we would show that kernel of T is the set x, y, z which belongs to R3 such that T of x, y, z is mapped to the 0 vector in R3. So by the definition of linear transformation, we can write this as x plus y equal to 0, which is equation 1, and y plus z is 0, which is equation 2, and z plus x is 0, which is equation 3. So after this, we can write this term as x equal to minus of y from the first equation, and y equal to minus of z from the second equation. Similarly, z equal to minus of x from the third equation. So we are letting that let x equal to k. That means from the first equation we would get that y equal to minus of k. Now from equation 3 we would get that z equal to minus of k, and again from 2 we would get that y equal to 2. This implies that we got that y equal to k and y equal to minus k. Since this is possible only for k equal to 0, this means x is equal to 0, y is equal to 0, and z is equal to 0 is the solution of the system. That means kernel of T is nothing but the 0 vector itself. By the rank nullity theorem, we can say that range of T is rank of T is 3. So let's verify why is the rank of T 3. What we know that the range of T of x, y, z is x plus y, y plus z, and z plus x. Since 1, 0, 0, 0, 1, 0, and 0, 0, 1, these vectors are the basis vector of R3. So T of 1, 0, 0 is 1, 0, 1, T of 0, 1, 0 is 1, 1, 0, and T of 0, 0, 1 is 0, 1, 1. So this T of the basis vector, the set T of the basis vector would be the spanning set of range. That means if this is a spanning set of range, since these three vectors are linearly independent and it is a spanning set, by the definition of basis, we can say that this is a basis of range of T. Since this is a basis of range of T, we can say that dimension of range of T is 3. So we have proved that by rank nullity theorem that we got dimension of image of T is 3. It is true. So in this way, rank nullity helps us in many ways. So let's see some more examples of it. So now we are going to discuss this application. Rank nullity theorem also helps us in finding a basis for the null space. That is, the rank nullity theorem is to find a basis for the null space that is kernel of a linear transformation. We can perform row reduction on the augmented matrix A0 to find the pivot and free variables, and then express the null space as a linear combination of basis vector. Before explaining this, I would like to share that every linear transformation can be expressed in the form of matrix. So given any linear transformation, we can write that linear transformation in the form of matrix. So, and after writing that transformation in the form of matrix with the help of row reduction, we can find the rank of the matrix. After finding the rank of the matrix with the help of rank nullity theorem, we can find the nullity of the linear transformation. After finding the nullity, the nullity would be equal to the number of free variables. And after finding the number of free variables, we can find the basis of the null space. So again, we can express that basis as a linear combination of this basis vectors of the null space. So in this way, rank nullity theorem helps us to find a basis of the null space. Now, second application, dimension of column space. Rank nullity theorem also helps us to find dimension of column space. Since I've already told that every linear transformation can be expressed in the form of matrix, so the range is nothing but itself the column space. Therefore, dimension of range of T should be equal to the dimension of column space, which is equal to the number of linearly independent columns. So, this application says that the theorem can be applied to find the dimension of the column space, which is nothing but the range of a matrix. The rank of the matrix is equal to the dimension of its column space. So, in this way also, the rank nullity helps us. Now, we'll discuss the other application, that is to find the rank and invertibility of a linear transformation. The rank nullity theorem is often used to determine whether a matrix is invertible. If the rank of a square matrix equals its sides, then it is full rank and invertible. So what we mean by square matrix is matrix of order m cross n, where m and n are equal. So if rank of a square matrix is equal to either m or n, that means the rank is equal to the dimension of domain. That means kernel of T is 0 by rank nullity theorem. So if the kernel of T is 0, then there is a theorem says that if the kernel of T is 0, if and only if T is 1, 1. So our the linear transformation is 1, 1. And since here in this case, rank of a square matrix equals its size, that means the range is equal to the codomain set. Therefore, it is onto. It is the linear transformation is 1, 1 and onto. Therefore, we can say that it is invertible. In the lastly, we have this, that linear independence and span. It can be used to determine the linear independence and the span of a set of vectors. If the rank of a matrix formed by these vectors equals the number of vectors, they are linearly independent. Otherwise, they span a subspace of lower dimension. So, this statement means that if we are given n vectors and we are to show that these n vectors are linearly independent, what process we would follow? We would write these n vectors in the form of matrix and we would find its rank. After finding its rank with the help of row reduced method, if the rank is equal to the number of vectors, that is n, then we would say that these vectors are linearly independent. Otherwise, if the rank is less than the number of vectors, we will say that they span a subspace of lower dimension. So these are the applications and the proof of the theorem of rank nullity theorem. I have taken my reference from linear algebra by S. Kumarasan sir, higher algebra by S. K. Mapa, and Wikipedia. Thank you.
Okay, thank you, Mamta. So, is there any question?
Yeah. In your last application, why did you use rank nullity theorem? In your last application?
Sir, in this, this similar to the third application I have shown, that the rank is equal to the number of linearly independent column.
Yeah, actually, what you could have said that you can determine how much less they are generating. I mean,
Ye-
once the dimension decreases. You could have said that. Yeah, I understand. Another thing, in the starting, you started with the basis of kernel of T. In the
Yes,
starting.
sir.
So you defined also that kernel T is a subspace, then there is no problem in defining kernel dimension at all. So my question is, how do you know that this kernel has a basis or a vector space has a basis?
Sir, since it is of finite dimension,
Okay.
we can say that it has a basis.
Like, can we give a outline? Just intuition, maybe.
Sir, I guess that would be my answer, that since it is finite dimension, we can say that there exists some basis.
Yeah, I'm asking like some intuition for that. So you are aware of that whatever comes in the basis that will be finite, right?
Yes, sir.
In case that. Why don't you start with a non-zero vector? Take a non-zero vector, take its span, then take some vector outside of that span. Are you getting what I'm saying?
Yes, sir.
See, say you know that there will be finitely many elements in the basis. By finite dimension, you know that finite, but you don't know at all that there is a basis one way. So you can give existential proof, or you can say that okay, have it. This is the basis. Here in this case, you can do this one that you can produce a basis, right? Produce a basis. You start with a non-zero vector. Then take its span and take another vector which is not in its span. Say you have started with E1, then you are choosing from V minus U1, span of U1. If V minus span of U1 is empty, then you are done. Your dimension is 1. And the singleton U1 is the basis. If not, then keep on choosing like that. Like V minus span of U1, you take U2. Then U1, U2, that's a set. Again, you start like span of U1, U2. P minus span of U1, U2. If that is non-empty, then take U3 from there and go on. Because it's a finite process, you already told that V is a finite dimensional vector space. That means this process has to stop somewhere. Where it stops, you get U1, U2, UN. This is your basis. No?
Okay, sir.
Yeah. And what about infinite dimensional?
So its basis also was the of infinite dimension.
Yeah. I mean, it should have a basis. No?
Yes, sir. But it would be of
So my question is, every vector space has a basis. This statement, I mean, in particular, finite we have seen, but finite also it is true, no? That it has a basis.
yes, sir. It is true. Yes, sir.
Okay, so viewers may go into its proof. It's an interesting proof that even if infinite dimensional vector space, they have a basis. Okay, I'm done, Jyoti.
Okay, any other questions? Okay, so we have no more questions. So thank you, Mamta, for your presentation.